All right. A little bit of a late start because we're chatting. Well, I was chatting. Nobody else was. So we were doing a couple more regression things on Tuesday. Specifically, we were looking at generalized linear models. And just a recap of generalized linear models. This is actually, it's something you should kind of keep in your head when you think about regression or things that you can solve problems with. Generalized linear models are going to be one of the powerful ones. If you have a set of labels or a set of something you're trying to predict that you know follows some sort of distribution, such as if you're trying to predict a classifier, a flip of a coin, you know that follows probably a Bernoulli distribution. General regression follows sort of a normal distribution if you assume a sort of error function. We talked about the Poisson distributions for estimating counts of things. If you have a situation like that, generalized linear regression provides you this nice mechanism where you don't predict the actual value, you predict the parameter of the distribution for any given input x. So if you have an x of 3, it gives you a value for the parameter for the Bernoulli, and then you can sample from that or just take the maximum, the most likely thing. But it provides this really nice probabilistic framework. It's a really powerful technique. Almost all classification at a high level is probably, if it's not using trees of some sort, they're probably doing logistic regression. That is a workhorse of classification nowadays, and that includes classification. It includes things like predicting click-through rates. That's a real common task, like if you're doing any kind of work with ads, with videos, with Netflix, trying to figure out who's going to click on their stuff. You're always trying to figure out whether somebody's going to click on something. That is probably using, there's a good chance it's using logistic regression because it gives you this nice probability of what's the probability of this happening. And then because it's a probability, you can actually chain it together with other things. So you can do things like, you could say, I want to predict what's the probability of them clicking on something, and given that they clicked it, how long will I watch it? And then you can get an expected watch time. For any of these sort of video sites, that is a huge thing for them. YouTube, I know we did it all the time, but you also did it for, like Netflix does it, Hulu does it. Anything where they're trying to figure out what to show to you, they're probably calculating it through some sort of logistic regression. So these are real powerful things. It is by far one of the most powerful techniques. And notice it's called logistic regression. You're not actually doing regression, you're doing classification, but it's regression under the hood to learn that one parameter. So we're going to move on today to a couple more small topics in regression, and then hopefully we'll actually move on today into some stuff that has to do with sequence models. So the next big thing in regression, something that we didn't talk about, we talked about previously L2 regularization. So L2 regularization, if you remember, we came along and we had, if we looked at our, where am I? If we looked at the residual, or rather the formula we used to compute the cost of making an error. So this is what we're going to minimize. This is the loss function. For an individual example, we often use the square of the residual. So that works out really nicely. But we talked about how, first of all, it's not a unique solution. There's some problems with when you actually work through the math, you get some poor behavior on beta. So we might want to add something like this, a regularizer that comes along, and not only does it make it a more unique solution, it conditions the that sort of covariance-like matrix that we ended up getting when we minimize this, so that it doesn't have small eigenvalues, so it's much more stable. So this is a good thing in general. You really want to do some sort of regularization. This, however, doesn't, it has one, not flaw, but one thing that it doesn't do that you really would like to do. When you do this sort of thing, it doesn't get rid of features. If you have 1,000 features and you do L2 regression, all of those features are going to have some small non-zero weight. Now, the reason it doesn't get rid of features very well is because the penalty is quadratic. So the penalty for you that you pay for having a weight of some sort is quadratic. So what this means is that if you have a feature, a beta, let's say it's beta 3 that's out here, you're paying this amount of penalty due to the L2 regression. If you have another beta, I'm making these betas up, you're paying this amount of penalty. So here, this the y is the amount, the amount of penalty that you have to pay. And what you see is that once the betas start getting closer to 0, because there's a square here, you pay less and less of a penalty for small things. So if you, if the system has to sort of push things around, it is much more likely to try to push beta 3 this way than it is to push beta 5 that way. It's not going to push those small ones towards 0 because they're already, have a very insignificant amount of sort of penalty to them. Now it'll push them towards 0. It just, once they get really close, they're definitely not going to zero out. So if you want to do something like feature selection, where you give it a big model and you want it to sort of drop a bunch of features that might be redundant or unnecessary, you want something that is actually going to behave in a different way. And that's where L1 regression comes in. L1 regression is not very symmetrical, apparently, but L1 regression is just you pay the cost without the quadratic on it. So you always pay sort of this linear cost. So you always get something out of, if you move, if you're playing the linear cost here, and you move beta a little bit this way, or you move this beta this way a little bit, or this beta the same distance this way, you receive sort of the same benefit from it. So it has a tendency to get rid of, to drive features to 0. This logic doesn't really show why that is. There's this very complex theory, not that complex, but it's hard to describe and hard to understand, that has to do with the sort of how the error function is shaped and how you're always sort of going to push one feature down to 0 before you push another feature down to 0 before you push a third feature down to 0. So you kind of have this work where it will come along and it'll push the smallest ones to 0 before it tries for the next one to push to 0. So it'll kind of iterate and push those feature after feature down to 0 before it starts pushing the next one. Now that's all constrained by, you also have to do a good job on the regression itself. But assuming that there's two options that are both good regressions, one which pushes a feature to 0 and the other one which doesn't, L1 regression will generally push features down to 0. So what does this look like? So we can look at a new loss function. So this is the loss function. We'll put a little 2 down there to say that it's L2. The loss function for L1 is we use the same squared error here. But instead of using the L2, we use the L1 error on beta. And that L1 error is just the sum of the absolute values of the individual betas. So if you add up all of the values of beta, all the weights of beta, that's the L1. I seem to be a little off kilter there. So this has a very different behavior than the L2, as I just discussed. The one thing about L1, it's very, very beneficial in a lot of cases. However, one problem with L1 is this is not differentiable. It turns out that we can't we can't differentiate that L1 term, and so minimizing this is actually much, much more complicated than simply taking the derivative, setting it equal to 0, and getting some nice linear system that we have to solve. So when we solve L1, things that have L1 normalization in them, or regularization, we have to play some games. And it's actually, the techniques for solving them are actually fairly complicated. We're not going to go into them. One of the nice things about them is it's actually more costly to do an L1 regression in general than an L2 regularization there. But there's a nice fact that you can actually do a whole set of lambdas sort of at once. You can calculate the regression, the main part of the regression, and then try bunches of different lambdas sort of with the same amount of work. So L1 is a little more expensive to compute, but you do get a nice property that you get a bunch of, you could test a whole range of lambdas. So let's look at what this means if we look at these are charts that we've seen before. This is the trade-off of sort of, if you vary the lambda from something, this is actually log lambda, but if you vary it from something very small to very big, you can see how the mean squared error changes. And when we're really small, you aren't making much of a difference. You aren't applying much regularization, but you are applying some. And what you see is that this is where you're going to get your smallest amount of error. Now, as you apply more and more regularization, you're forcing it to sort of make mistakes in some way on the data in order to sort of cope with that regularization term. And so that's what you sort of see here. As you increase your regularization, the weight of your regularization terms, you actually do worse on the data set, and you get a little more variance in the measurements. But it has that nice it has a nice property that it's actually forcing features to 0. So across the top here, you can actually see that this particular graph had 10 input variables. So we had 10 total variables. Down here, when the regularizers were really small, the value was really small for lambda, we kept all 10 features, meaning all 10 features had non-zero weights associated with them. However, as we pushed lambda up, we start seeing exactly what we want. Over here at this point, we're down to 8. Over here, we're down to a single feature. Now, maybe that's too far. Maybe we had, we need all 10 features, and that's why lambda has to be so big. Sorry, lambda has to be small to get to include all the features. But in some cases, you may not want all the features. A good example of this is something where you have more features than data. So there's a set of problems where you might have, 10,000 features, and you only have 1,000 pieces of data. Now, if you have that sort of situation, your problem is obviously under constrained. You almost always want to have, you always want to have more data than you have features. In fact, you usually want to have much more data than features. And so you're in a situation where you have lots and lots of features and very little data. L1 allows you to deal with that. It'll allow you to sort of zero out features that don't seem to be important and only retain a small subset of the features. And then, once 500 of the features are zeroed out and you only have 500 left and 1,000 pieces of data, you're fine. Before you had 1,000 pieces of data, 1,000 features, you probably were in a bad place if you try to do something like L2. So this is a real common technique for dealing with that sort of thing, and just to induce sparsity in your models, which sparsity is just generally considered a good behavior to have fewer features in your model. There's no way to really prove that it's better or worse. It's just considered that if you can have the same performance with fewer features, it's a simpler model and it's probably going to generalize better. There's one more graph here we should look at. This actually shows the, this is a graph of the size of the individual coefficients. So each different line is a different component of beta. And then the effects that lambda has on those. So what you see is that there's this one feature that has a really high coefficient. Either it's scaled poorly with relation to the other ones, or it's a really important feature. And you can see that it definitely gets pushed down quite quickly as lambda starts going up. Here we can look at, on the right-hand side here, this is just zoomed in. So instead of going from 0 to 50, this one goes from 0 to 10. So you can see how they kind of, all of the features, we can just blow them up and look a little closer at what they do. And you can see all of them are kind of, sort of getting pushed down towards 0. And it's sort of, they all sort of have this behavior that they they're kind of level, and then they sort of dip right at that end. And that's where it sort of chooses, I'm going to start pushing that feature down. So this is a pretty common behavior. This is exactly what we want out of L1 regularization. Now, one of the downsides of L1 regularization is if you have correlated variables, it has a tendency to choose one of them and push all the weight onto that one variable and zero out the other variable. If they're highly correlated, they're both sort of providing the same, mathematically the same, they have the same purpose. They're kind of providing the same support for your function. So you can, if they're highly correlated, you can push the weight of one down to 0, double the weight of the other one, and you get the same, same prediction as if they both had, half of the weight apportioned to them. So L1 has a tendency to just sort of arbitrarily choose one, push one to 0, elevate the other one in order to compensate. That's not always a good strategy. Even if they're highly correlated, it sometimes makes sense to sort of have a balance. If you have two features that are highly correlated, you want them both to sort of have half of that weight. It's not always necessary. If you really want sparsity, you might want to avoid that. But we can avoid this issue by combining L1 and L2 regularization. So our loss function for 1 and 2 is going to be, again, just our square residual. And then we're going to have a lambda factor. And now we're going to have the two forms of regularization. Okay, so L1 and 2 is just the error that we write out all the time, the squared error. The lambda, and now we're going to have some, we're going to have to balance between the two types of regularization. We're going to have both L1 and L2. So we're going to have another hyperparameter, alpha, which is going to control the distribution between the L1 and the L2. So you still have lambda, and lambda controls overall strength of the regularization. And then you have alpha, which basically takes the proportion of whether you're doing mostly L1 or mostly L2 or sort of an even mix. If you push alpha down to 0, then you're doing L2. If you push it down to, if you push it up to 1, then you're doing L1 only. So it gives you this nice sort of balance. Now, of course, it is another hyperparameter, which means that you, if you want to tune this, all of a sudden you have two hyperparameters to tune. You not only have to tune your lambda, but you have to tune sort of the balance between the two types of regularization. So you can do that with normal cross-validation, just like we always seen. It's just another parameter. I have seen this used. I don't know how often it's used actually in practice. I have seen both of them used. L2 is by far the more common thing to use, but it really depends on what you're trying to do. If you want sparsity, you have to use L1. But if you don't want sparsity, if you don't care about sparsity, then most people use L2. Is there questions on that? These things have names that come from basically the statistics background. L1 is always called LASSO, L-A-S-S-O. L2, when you do just L2, that's called ridge. And and if you do both of them, it's called elastic net. You don't use those terms all that often, but you will occasionally hear, especially people who are coming from a strong statistics background, will use terms like ridge regression, lasso regression, or elastic net regression. And that just specifies what kind of regularization they've put on their regression. Like I said, you don't hear them too often, but you run into them enough that it's good to know what they refer to, or that they at least refer to one type or another. Okay, any questions? Cool. All right. Okay, so that's it for regression, or sorry, for regularization of regression. Just some quick comments. The next part we want to talk about, which is a fairly major part of regression, but we're not going to spend a lot of time on it, is the use of sort of a nearest neighbors to do regression, and then in addition to that, something we call kernels, which is sort of a generalization of nearest neighbors. So let's look at one example of nearest neighbors, which is kind of interesting. There we go. Okay, so regression in general, you're predicting a value, a single value. But what we found when we did nearest neighbors previously with classification is that you find the nearest neighbor and you can actually do things that used a more structured sort of data. And so in this case, we actually have a pretty interesting example of somebody wrote this. This came out maybe 10 years ago. At the time it came out, it was like amazing that they could do this. Like this was a major paper. But what they actually do here is they actually use a nearest neighbor algorithm. You take an input picture that has some stuff in it you don't want. And you basically get rid of that stuff. You chop out this sort of patch. And so you see the initial image down here. This has this house that's blocking your view. You don't want that in there. And so you could come along and chop this patch out that you want to get rid of. And then you go to the internet and you collect millions of images. You just find all sorts of images. And you use that as sort of a dictionary to map against this picture that's been chopped out. And so you take this picture and you find its nearest neighbor among all your catalog of different images. Now everything has to be scaled correctly. They have to be the same size. They have to be sort of, there's a lot of pre-processing you might have to do to get this to work. But if you find the nearest one, then what you can do is you can take this chunk of the image that you want to replace, and you can steal it from the picture, this picture that you found, which happens to be this one right here, and you can create this new picture that totally has something different in it. This was a pretty revolutionary thing. When we started getting, this is like an example of what you can do with sort of the big data idea. Big data just means you have a lot of stuff. If you have enough pictures, you could probably find one that is close to the picture you're looking at. And this is a really straightforward nearest neighbor. Now it's expensive to compute. You have to do these, a comparison of all these images with each other. But what you end up with is this nice final image that looks mostly real. If you stare at this for a while, you'll probably notice that things like the shadows are probably going in the wrong direction. The perspective is slightly off on the boats. There's a bunch of little things that you might be able to figure out that makes it look a little odd, but it's still pretty good. So that's sort of the first comment on things you can do with nearest neighbors. This is you end up this ends up being very specialized, however. So now we're going to talk a little bit. We're going to move a little bit into the more standard approach to nearest neighbors, just to predict a single value. So what we're going to want to have is we're going to have some input, which is a bunch of x's and their y's, and then we're going to look at sort of how to do the nearest neighbors. The biggest problem with nearest neighbors for regression, the most straightforward thing you would do is you'd find the nearest neighbor, and once you find that nearest neighbor, you'd basically compare a new x to all the existing x's, and once you find it, you would return the y that's associated with that value. The problem with that, and again, we're talking about y's that are scalars now. The problem with that is that if you do that, you end up with a piecewise function. Because you end up, if you only have a couple pieces of data, let's say you have this piece of data, this piece of data, and this piece of data. So any value over here is going to be the nearest neighbor to this guy. And he'll return, this is your y value, and this is our one-dimensional x value. For any neighbor over here, this is your nearest neighbor, you return this y value. So you end up with returning this value. For anybody in this middle section where this is the nearest neighbor, you end up returning that value. And anything over here, you end up returning that value. So you end up with a piecewise function if you do that, which can be useful still, but it doesn't really adapt well to the changes. Now you can start doing things like using the two closest nearest neighbors. That doesn't help the problem though, because if you use the two closest, let's say you use this one and this one, that means when you're sort of in between the two of them, you're taking the average of their values. When you're in between these two, you'll take the average of their values, which is, I don't know, something like that. And possibly at the end, you take the average of their values, depending on how you wrote it. So you still get a piecewise function. Now, it might have more granularity, but it's always going to, however many neighbors you're considering, there's still always a hard, sort of a hard edge of when you add a new neighbor, you replace this one neighbor with another, and you get the new value. That has a sort of a hard edge to it. So of course we've seen this before. This isn't the best strategy if you need something that's smoother. And so what we end up doing is we end up coming up with a weight. So instead of just doing an average of the values to get your prediction, you weight them according to some distance. So we're going to take I'm not sure why we switched to U in the book, but we did. So we're going to take some k nearest neighbors, and and we're gonna find the k nearest neighbors. We are then going to take their values, weight them according to how far they are from the query value and the neighbor, the x value of the neighbor, and then we have to normalize that. Again, u equals 1 to k, just over the weights. So this is now a weighted version where we've smoothed out all of those edges. Now, as you get, you still have a little problem that if k is a small value, you'll be adding and dropping k's and getting some sharpness to your function. But if k is big enough, all of a sudden you've created this nice smooth value or smooth estimation over all the neighbors, which is exactly what you kind of want. Now there's a couple different. We now have this weighting function, and there's a couple different ones that you might want to use. The two common ones are two common ones. I don't know if they're the most common, but there's inverse distance. This is just what it sounds like. It's 1 over the distance between the points. It can be squared or it can be not squared, doesn't matter really. So that will just drop off sort of inverse to the distance. The other common one is, of course, the Gaussian. It drops off in a slightly different way, but still has very similar behavior. And with the Gaussian, you now have, you also have a hyperparameter, this guy, which controls sort of the width of that weight measurement, how quickly it drops off. So you can, the smaller that is, the more quickly the weight will go down to 0. So you get kind of this, the nearest neighbor doing this, you get a nice smooth, you can get some nice smooth values. Of course, it's at the trade-off of a lot of computational cost. So let's see if we have some examples of this. All right. Okay, so here's some examples. This is basically, I think this is just fake data for a sine wave of some sort. And we did the very upper left. What we basically did is we took we're showing that piecewise behavior. There are some sort of diagonals on this particular graph, but that's more of an error in the graphing methodology than in the actual. There are no actual lines that are going at an angle in this graph. It's just the way that the plotter is showing it here. So there's all hard edges as you go between points. So this is definitely not what you want. And so the first thing we can do is, we can take multiple nearest neighbors, and that will give us for smaller chunks. And then we can apply the different weighting factors. And so what you end up getting is some pretty nice, fairly curvy things that sort of match what you would think out of a sine wave. So they're not perfect. You could see that they have some sort of, some of them are a little bit slow to move. Some of them are too fast to move. That's really as you adjust that hyperparameter, the sort of the sigma, you're really changing how quickly they adapt as opposed to being sort of spread out farther. We could see another example of this, I believe. down here where you can see how it has some nice ability to actually sort of model the data, even when the data is a little bit odd. Now, arguably, this might be a poor model. I'm not sure how well I would believe that this generalizes. It's more of an illustration of what this technique can do. One of the problems with nearest neighbor is that when you're in areas with very little data, then you end up with a pretty high variance estimate. And so what we're actually seeing here is he drew some lines that show kind of if you took a different data set, how much variance do you get in the predictions. And what you actually see is that places where there aren't many data points, you start getting a lot of variance. And that's probably a sign that your estimate's pretty bad, that it's pretty unstable. This is actually, for what it's worth, a trade-off of sort of the bias variance that we talked about. We really, using a nearest neighbor, you provide very little bias. It has a really low bias sort of algorithm. So it's able to really conform to your data. But the downside of that is that it has high variance. So you end up with this algorithm that if you change the data just a little bit, the estimates move quite a bit. As opposed to when we were using just a quadratic, a linear estimator with a quadratic feature in it, and it got this nice smooth curve. The variance there was very low, but it definitely had more bias. Now it happens to fit this particular set of data pretty well, but there was a strong bias that it could only have this nice one curve to it. So that was kind of this is kind of one of the downsides of nearest neighbor. Of course, the other downside of nearest neighbor is that it's expensive. Nearest neighbor is something where every time you get a new prediction, or every time you get a new example that you need to predict, you need to basically compare it against every single example you have. Find the k nearest neighbors, calculate, you have to calculate all these weights, you find the k nearest neighbors, then you average all the values together. The more data you have, the more intensive it is. Whereas most regression algorithms, you pay most of your processing cost up front when you train the model, and you only pay a small portion to actually calculate the prediction. So nearest neighbor is expensive, and that's one of the big problems with it. I wanted to make one more comment about regression that's related to nearest neighbor. So one way to deal with this explosion of data is to not use all of your data. And so what you come up with is you choose some subset of your data, and you use only those data points to actually represent your regression. And often this is called using kernel functions, which is what we've basically been doing with weights. You should know what a kernel function is just because they come up enough, but they're not as popular as they were once upon a time. But they still you'll hear them from time to time. So a kernel function, k is a kernel function if, first of all, it has to be greater than 0. You guys are lucky I look up a lot. It has to be greater than 0. It has to be symmetric. If you change the sign of the input value, it's the same as, the positive is the same as negative. It has to sum to, over all the values, it has to sum to 1. So that's a pretty standard, it's the definition of a kernel function. This is a pretty standard thing to use. And what we'll find is that a common kernel function is the Gaussian. The kernel of the Gaussian is just what you would think, except slightly simpler than the we usually write the Gaussian out as. So it's just u, which is basically your distance from whatever the center of the value is. There is no sigma here. So that's the Gaussian kernel function. Now, the one thing about kernels is, you could prove it mathematically, is if k is kernel function, then 1 over s k u to the s is also a kernel function. So you can just rescale them, basically is all this is saying. You can just take them, rescale them, and rescaling them is the equivalent, doing this to this, is the equivalent of basically having a sigma, that's a very drunken sigma, there you go, is basically the equivalent of having a sigma that you can adjust that scale. So that's how you kind of get away with not having sigma on this particular definition of a kernel function. It's just because you can arbitrarily rescale your kernel functions. Now, the kernel functions, if we go back to this guy, and we're talking about this weight, these weights are actually kernel functions. So this is actually the exact same thing that we just used, except that we applied a normalizer of 1, the square root of 2 pi, to the front of it. But this is just the Gaussian kernel with x minus xu as the input. So kernel functions are just ways of reweighting stuff. And you can kind of think of kernel functions as a way to sort of build up a regression from a bunch of what are called basis functions. So what you can view kernel functions as, and you can view nearest neighbors in the same way, is that you'll have a bunch of kernel functions, except they're symmetric, not wavy like that. And you can kind of, by adjusting sort of the distance between each of the centers of the kernel functions, you can get this nice sort of regression that ends up sort of like that. So that's conceptually how you should think of kernel functions, is that they're a bunch of things that sort of add together to build up a regression. We actually see this, we got an example of this. Let's see if I can find a good one. No, not a great one, but here we go. So this is actually an example. This is a bunch of, it's a bunch of samples of, I believe it's the number of catches of prawn given some latitude and longitude. So you get kind of, you can see how, this is actually, plotted in 3 dimensions here. And you can see how there's a bunch of, let's see how big I can make that. You can see that basically there's a bunch of little bumps here that when we want to make an estimate, we're going to add them all together. Now, in this particular case, we used bumps that were fairly small, like they're very steep. And so you end up in a situation, this is the heat map for that. You end up in a situation where it's not very smooth, where small changes between, between where you are result in these big dips and jumps. If you take your kernel functions and you make them, wider, if you spread them out, you change that scaling factor, you'll end up in a situation where this is a much smoother thing. And I think we do have one, like here's one where a fairly extreme example where we took those kernel functions and we made them very wide. And what you see here is that all of a sudden things are very smooth. Now once you have them down to be very smooth like this, you don't need nearly as many centers. So you can drop a bunch of your data essentially and use a much smaller number of kernels or basis functions. Those two terms will be almost always exchanged. And this allows you to actually get the benefits of nearest neighbor without paying all of the cost of, every time I have to categorize something, or every time I have to predict something, I have to go through 10,000 pieces of data. So this is kind of the idea behind kernels. It's kind of taking a bunch of these lumps, building up a function from them, very similar to weighted nearest neighbor, mathematically indistinguishable when you use all of the data. And that's pretty much all we're going to say about the kernel functions. They're a very useful tool in some cases, but they also can be kind of limited in the sort of their application, what they're able to do, in that they get very computationally expensive, and you're really limited to a fairly small number of kernels. Kernel functions also have a problem that as you get away from your data, your estimates have a tendency to sort of go down to zero. Because if you think about a bunch of bumps like this, wrong button. If you think about you sort of made this orange thing from a combination of these three purple things, as you get out in this regime and this regime, everything kind of tends towards zero. Just because you got too far away from any of your kernel functions, everything kind of zeroes out. That's a downside of them. You probably shouldn't be predicting stuff out there anyways. If you're talking about a linear regression, there's a good chance that it has some bad behavior out at the edges anyways. But it is definitely something that if you have a small number of kernels and you're far from the centers, your estimates start getting really bad really quickly. Okay, any questions on that? Okay, cool. Okay, we're done with regression. Regression is a pretty powerful tool. It's, like I said, it's the workhorse that almost everybody uses for, most of the non-esoteric sort of things that you do nowadays. So it's definitely something that you need to know and something you need to know how to use. It has a tendency to be something that you just take an algorithm, you push in the data, it plops out a model, you see if that model's good or not. There isn't a whole lot. I mean, there's tuning you do, there's a bunch of other stuff you do, but we could take a whole class that told you about regression, also for different types of regression. The book has a bunch of stuff that we didn't even talk about. In the end, if you know sort of logistic regression, sort of things like that, you're going to be doing pretty good. You don't need much more than that to sort of get started. Okay, so now we got a brand new topic. We're moving on. We're a little bit ahead of time, which is good because I wanted to add a little bit more at the end of class on neural nets. We're going to start talking about sequence information, sort of sequence data. So we're going to look at sequences of things and how to model them, what you can do to model them, what kind of predictions you can make, that sort of thing. So to start with, we're going to talk about something called a Markov chain. A Markov chain, let me just set it up like this. If we have a sequence of values, x1 up to xn, And these are, each one of these values is some sample from a random variable. So we're only going to consider cases where we're talking about discrete values. So now x is not a scalar, or sorry, x is not, it's not a scalar, but it's also not a vector. We're just going to be talking about, say, x being a letter or a word or a single integer from a finite set of integers. And we're going to try to model these things. Now, you can extend these to be real values instead of discrete values. The math is much more complicated, so we're not going to talk about that. You can also extend these. We're going to be talking about discrete time steps. So there's x1, x2, x3, x4. You can extend this theory out to have a sort of a continuous moving value. And there are extensions to that. That gets very complicated, so we're not going to consider that either. So we're talking about discrete values from a random variable. So basically, think of it, you have a dictionary of things that can be output, and each x is one of those things, a sample from that dictionary. And then there's a sequence of length n. So what we're interested in is sort of the probability of a certain sequence. And a Markov chain has this probability that the probability of xi given x1 up to xi minus 1. So basically the probability of the ith item in this sequence, given all of the past items that you've seen, is equal to the probability of the ith item given the I minus 1 item. That's basically the definition of a Markov chain. If you have a sequence of samples from a distribution of these random variables, and the probability of the ith random variable is only based on the item that came directly before it, then it's a Markov chain. Markov chains, once we're using Markov chains, we actually can do, there's a bunch of tricks we can do. These things are really good at sort of modeling sequences of things. So the biggest one that you'll see that everybody uses them for is text. All sorts of text models use Markov chains, or something we're going to call hidden Markov models a little further on. These are really common things to do. And it's just because if you know, sort of if you consider a sentence in English, if you know the word right before, you can actually make a pretty good guess of what the next word, the distribution over the next word is going to be. And we can play some games in order to look back more than one symbol. So this actually seems pretty limiting. So if I want to look back only a single symbol, it'd be really hard to generate an English an English word that would make English sentence that would make a lot of sense, because you'd only be going back one word. But we'll play some games in order to still have a Markov chain, but be able to look back a little bit farther into the history. But conceptually, you are always limited by how far you're going to look back. Let's look at one quick example of a Markov chain that somebody put together. This is a comic strip generator. What they did is they took all the Garfield comics, I think, ever. They extracted the text from them, and then they built a Markov chain, sort of predictor to generate new text. So if you know this probability of having your next word given your current word, you can generate the first word, given having no words. Then, given that first word, you can generate the second word. Given the second word, you generate the third. So you can build up a sentence just by following the probabilities. So that's what this guy did. He took all the Garfield comics. He figured out these transition probabilities. And he built this generator, and then he put a bunch of code to make it look nice. So if we reload this, we can see different things that were generated randomly. So as soon as Odie finishes rolling on the, and he cuts off, these people need help, my car payment is late, I'll never drink. Now, it doesn't make any sense. It's not going to make any sense. I think as he called them, this is semi-coherent text synthesis. You know, it doesn't quite make sense. I see you hit him again. The only. Z, I hate. I'm, and pity his stupidity. That was a particularly bad one. What about born to whine? Give me an F. Stop being silly. It says here to shake well before using. I don't know. These don't make any sense. So we can actually do a similar thing. Oh, shoot. Hopefully I didn't get. Let's hope this works. Otherwise I'll have to reload the whole thing. Okay, cool. So we can do a similar thing. I took the book. I took all the words in the book. I just split it all up. I counted basically, you know, I created these Markov chains where I looked at any given word, what the probability of a word following it is. I start with a random word and I generated some text. So you can see this one, you know, Q in the second and the left. You might wonder whether differences between any real number tells us to make mistakes more the wrong answer. By knowing which can find this matrix, imagine we can. Okay, it's kind of gibberish. This one is only looking back a single word. So it's actually what we call a bigram model. It takes one word back and then the current word that you want to generate. But we can look back further. Here's if we look back 2 words. Look back, the lowest one looks pretty good. Now take the value of b hat or beta hat of beta such that, remember this, most simple questions about programming can be colored because the 2 plots are stop splitting when there aren't many of them to produce a 6. Standard machine learning technique. And these are random, so we can generate, we use a decision tree. It is easy. For one data point, a separate cluster, your intuition should suggest, he says that a lot, your intuition, should suggest that the data in 2 pools by flipping an unbiased estimate of the split has the best. And I'm just generating. These are fixed number of words, so we could figure out where the things are. And you can actually see some of the biases here. So this was poor pre-processing of the book. It's just where there was a hyphen and clusters got split into 2 lines, and I didn't clean it up. But what you find is that if you looked at the probability mass, anytime you have plus and then a minus, it is always followed by the second half of the letter, or the second half of the word, because that's the only thing that ever comes after that in our data. So it can actually assemble things pretty well. You can see, you know, this is like 100% that it was going to generate that. It does the same thing with k-means. K- is always followed by means because sometimes it gets wrapped around the edge of a paragraph or the edge of a line. So, all right, so that's sort of the example of Markov chains. There's a lot of them out there. There's a bunch more generators. If we went up to quadgrams, whatever 4 of them, you actually will get very consistent sounding text. And it will start coming out very, you know something was wrong, like it wouldn't be semantically, but syntactically it would be very coherent. So you can do quite a bit with these. And they're kind of fun to do. So let's talk about how we might do this. So first of all, you can think of a Markov chain as basically sort of a state diagram that you're moving between. So this is one way to think about them, is that this is your is the current x you're in, and then you'll have some probability. So this would be sort of your xi minus 1, and then you have some probability of moving to each of a new state. So this would be, we'll call it A, B, and C. So if xi minus 1 was A, you have some probability of moving this way, some probability of moving this way. If xi minus 1 is, and that means you emit a B, basically. You go from an A and you emit a B. If you're in the B, if your last thing was a B, you have some probability of going to C, you have some probability of going back to A. Go that way and that way. So you could think of these as just those probabilities is just sort of a state diagram of moving around between the different states, given your current state. You can get these probabilities just by counting, typically. You can look at all of the times I was in state A and went to state B, and you can look at all the times I was in state A and went to state C, and then you can normalize by those counts by the number of times I was in state A, and you can get that probability. So counting is these are actually really easy to do the math to figure out what the probabilities are, given a large enough sample that covers sort of your whole corpus. So let's look at the differences between what we call unigram, bigram, trigram models. The first one we're going to look at is a unigram model. Basically, a unigram model is, and we're going to talk about letters. If the examples I showed here is if we treated each word as one of the discrete units. You could treat letters as discrete units. So you can move this down to generating words letter by letter. So I could draw a letter from some distribution over the letters, and then I'll repeat. And notice that this probability isn't conditioned on anything. When we're not conditioned on anything, we call it a unigram model. It's still a Markov chain because you could finagle the math so that it is conditioned on the past thing, but it doesn't matter what that past thing was. So you can still represent this as a Markov chain. Now these aren't particularly useful. If we talked about generating letters, generating words starting at the letter level for a unigram model, basically you're just going to get a string of the most common letters in English. So the first draw, maybe it's an A, an E, an A, an R, maybe there's an L in there, an A, an E, another E. You'd have a lot of A's and E's. E's are the most common, you'd have the most of those. But they wouldn't make words in any way because it would just be sort of unconditioned, there's no order to them, it's just the most common stuff. A bigram model is when things start making a little more sense. So now we draw L from sort of Li from the probability Li given Li minus 1. And then we repeat. Now to get the first letter, we don't have any previous anything, so we can either use a unigram model or, who knows how we generate this first letter. There's a bunch of different techniques depending on what you're trying to do. But let's say I generated an A as my first letter. Now I'm just going to sample along. Now given an A, all the other letters are going to have some probability. Maybe an R comes next. After an R, there's probably a good chance of, an E. After an E, there's a good chance of, C. After a C, there's a good chance of an H. You're going to get a string of letters that start looking like words. They won't be words, but they'll look like words. So that's a bigram model. And trigram model is what you would expect. You're going to draw Li from given li minus 1, li minus 2. If you did that, now you're going to start getting words that look a lot like English words. And they probably will be, that you will have a bunch of English words mixed in there. Now, you won't have long English words. You have a bunch of short English words. But a lot of the words you generate, if you generated a bunch of 5-letter words, I bet you half of them are going to be real words, or something, some high percentage of them will start being real words. Now, one thing you should think about is that we're actually using we're looking back twice now. So if we leave it like this, technically we're violating the Markov chain rule, but there's a really easy way to get around that. So if we look at a sentence, the cat had a hat. The way to get around that sort of cheating and looking back twice is just to redefine what you consider a single discrete random variable setting as. So instead of considering a single letter as a random variable, you consider the pairs. So each one of these would be a single symbol that we can predict. And then you have sort of this constraint that if you've already have a th, the only things you have non-zero probability are the things that contain an h to start with. And then everything else has a 0 probability outside of that. So this is just sort of a mathematical trick to make sure that there's still Markov chains. It gets kind of complex to do all the accounting when you start doing that, but it's very straightforward conceptually. Just say, well, we can't look back more than one. Well, we'll call two things one thing, and then we can look back. But from a real implementation point of view, you just look back two. As long as you're looking back a finite amount, it still will be a Markov chain if we just massaged it around a little bit. Okay. So we talked about that we could just count to get these probabilities. So you take all the transitions, you take the previous state, you count up all the places it's gone to. For unigram, well, unigrams are useless pretty much. For bigram and trigram, you're probably not too bad. But as you start going up into the number of how many symbols you look back, you're going to end up with a sparsity issue. So there's going to be a bunch of transitions that never occurred in your data. So that leads to a situation where if you have a new sequence that a sequence does come up in, so let's say the probability of, let's see, we never saw the sequence AZRN, and we have a 5-gram model. And all the probabilities, this never led to anything. So if I were to ever come along and get into a state where this was what I currently had as my sequence, I would have a problem. Because all of these would have 0 probability, and I wouldn't know where to go. So there's sort of this sparsity issue we have to fix. Now this does happen, this does actually happen. Like Google has gone out and they've read, basically every book in the world, and they built, I think, either a 7 or a 9-gram model of words. So they took all sequences of 9 words that occurred in all English language that they've ever read, which basically is every book, and they mapped out the counts. But there's still going to be sequences that have never occurred in any book ever. That might still be sequences that you could write. And so you do run into this in real literature, you do run into this problem where you have to somehow deal with this. One way to deal with this would be sort of our traditional, just add 1 to the count of everything. So if you had a bunch of things, and if you had, if you had this guy, this sequence, and then you had a bunch of, the A, the B, the C that you could extend it by, and they all count to 0, you could add a count of 1 to all of them. That's fine, you can do that. The problem is that if you had, let's say you had D here, and this did have a count, and then you added 1 to it. What you end up with, if this was your whole alphabet, you end up with a huge portion of your mass, in this case 60% of your mass, is going to end up in these things that never had counts, and only 20% is going to end up in the place where you actually saw some value at some point in time. The more sparse you get, the more that this will happen, that more of your mass will go to things that never occurred. So another sort of strategy to do this is you could just say 10% of the time I want to go, I want to distribute 10% of the probability mass out to things that have never happened. So you take all the things that have never happened, you give them 10% of the probability mass, you leave the other 90% on things that did happen. You could play games like that. Really, that's not a great thing either. There's really no good way to do this that's going to be perfect. It's going to depend a lot on what you're trying to do. One way to do this is if you don't have an entry for this, you could look at instead of looking at the 4 gram there, you could look at the 3 gram. If that never occurred, you could look at the 2 gram. You could kind of look backwards at a smaller and smaller window to get a better estimate of how to go forward. Okay, so that's all we're going to talk about with Markov chains. That's going to be the basis for what we're going to do next week, which is hidden Markov models. Hidden Markov models are pretty cool. Early speech recognition was always based on hidden Markov models. They have a bunch of usages in DNA sampling and sequencing, in noise elimination. So for sequences, they're a very common used thing. And they're pretty interesting. So we'll do that next week. Any questions before you guys go? Okay, cool. I'll see you guys next week. It's not